In order for a proof by mathematical induction to be valid, the basis statement must be true for n equals a, and the argument of the inductive step must be correct for every integer k greater than or equal to a. In 45 and 46, find the mistakes in the proofs by mathematical induction. Now, they put quotations around the proofs because these are not actually correct. So the theorem in this problem is for any integer n greater than or equal to 1, all the numbers in the set of n numbers are equal to each other. Now, the reason why this theorem is in quotes is because it's false. This is a false statement. I can have a set of 5 numbers that are not all equal to each other, like the set containing the numbers 1, 2, 3, 4, 5. So this theorem is definitely false, which means this proof is definitely not a proof. So let's try to figure out what's wrong with it. It is obviously true that all the numbers in a set consisting of just one number are equal to each other. So the basis step is true. Now, that is correct. Whenever you have a set of size 1, that's called a singleton. And in every singleton, all of the numbers are equal to each other. And so that part is definitely true. So now let's get to the inductive. Let A be the set a sub 1, a sub 2, all the way up to a sub k plus 1, be any set of k plus 1 numbers. Form 2 subsets, each of size k. So we start from a sub 1 all the way up to a sub k, and a sub 1 all the way up to a sub k plus 1, without a sub 2. By the inductive hypothesis, all the numbers in B equal a sub 1, and all the numbers in C equal a sub 1, since both sets have only k numbers. Now, the problem with this is very, very subtle. Now, the inductive step must be correct for every integer k greater than or equal to a. A, in this case, corresponds to the base case, and the base case consists of a set containing just one number. So that means in the inductive step, k has to be at least 1. So let's imagine k equals 1. What would be my set B and C? Well, B starts at a sub 1 and goes all the way up to a sub k, which would be a sub 1. And that would mean B is just a sub 1. My set C would be a sub 1, a sub 3, a sub 4, all the way up to a sub 2. But that's a problem because it says here that all the numbers in A except a sub 2. So what would my set C be for k equals 1? Well, it's impossible to know because if k equals 1, then this last term would be a sub 2, even though that's technically impossible since this is a sub 3, a sub 4, all the way up to ... a sub 2. What does that even mean here? So let's summarize what we've shown. We've shown that P of 1 is true. That's correct. We've also shown that P of k implies P of k plus 1, but only for integers k greater than 1. We did not show that this implication is satisfied for when k equals 1. In fact, P of 1 does not imply that P of 2 is true. So it is true that P of 1 is true, and it is true that the truth of P of 2 implies the truth of P of 3, which implies the truth of P of 4, and so on. That's also true, but we're missing a huge link from P of 1 to P of 2, which means that P of 2 might not be true. And if P of 2 is not true, then that means that P of 3 might not be true, which means P of 4 might not be true, and so on. So the fact that we don't have this implication here that connects from P1 to P2, that means that this proof is not sufficient. There's actually a Wikipedia article that explains this very well, and it's a falsitical paradox that arises from a flawed use of mathematical induction. And it's this exact same flawed use of mathematical induction. So if you want to understand this subtle issue here, it's very much worth it to look up all horses are the same color. It's an absurd statement. It's definitely false, but the proof will look correct unless you have a very well-rounded understanding of mathematical. Thanks, everyone, and I'll see you in the next video.